In the first part of this question, we express the population of the colony of rabbits, that is P of t, using this population model given by P of t equals P naught e raised to the kt. So this is the generic population model. It is the whenever the population grows exponentially. And so here we are given that P naught, which represents the population at the beginning, is 15. That is, there are 15 rabbits at the beginning, and they grow to 400 rabbits after 5 years. And in this case, we have to write down the population at any time t, that is P of t. So let's plug in P naught equal to 15, and this one is e raised to the power of k times of t. This one is the population model. However, we can utilize the other condition, that is after 5 years, P of t equals 400. So here we have to determine the value of k. For that, we will use that condition. So I'm going to plug in t equal to 5 here. That is, it becomes P of 5, and this equals 15 times e raised to the power of k times of 5. And P of 5, this one, if you replace the t equal to 5 here, it becomes P of 5 equals 400. So let's replace P of 5 by 400, and this equals 15 times e raised to the power of k times of 5 is 5k. We have to solve for k from this equation. First, let's divide both sides by 15. So we get 400 divided by 15, and this equals e raised to the power of 5k. To solve this type of exponential equation, we generally apply natural logarithm to both sides. Therefore, we get natural logarithm of 400 over 15, and this equals natural logarithm of e raised to the power of 5k. The next step, we see that we can apply the power rule of natural logarithms. And in that situation, this 5k, which is the power of the exponent, this comes into the front. That is, it gets multiplied with this natural logarithm of e. So in the next step, we can write down this as a 5k times natural logarithm of e as the right side expression. We must be knowing that the value of a natural logarithm of e equals 1, and this means we can take this off from the equation, and so we are just left out with 5k on the right side. On the left side, we have a natural logarithm of 400 over 15. So solving for k using this equation, we get k equals natural logarithm of 400 divided by 15, and this is divided by 5. We put this expression on the right using the calculator, and when we do that, we determine the value of k. This is approximately 0.6567. This is rounded to 4 decimal places, and this means we can now go back and substitute into the model, so that we write the population of the colony of rabbits after t years. So we write P of t equals 15 times e raised to the power of replace k by 0.6567. So it is 0.6567, and then multiplied with t, so it is 0.6567 t. And so this is the model which represents the population of colony of rabbits after t years. In part B, we determine the time it takes for the rabbits to grow to 1000 rabbits. So using this graph of the population, so here we have the graph of the population, which is graphed over here. So this one is the vertical axis is the P of t, and the horizontal axis is time axis. This one graph, which I have shown in green color, is the graph of the population. P of t equals 15 e raised to the power of 0.6567 t, representing the population of rabbits after t years. And so we can see from this point, that is when t equals approximately 6.395, the population is 1000. So therefore we can see that when t approximately 6.4 years, this one is rounded to zero point zero 0.01 year, we see that the population grows to 1000 rabbits.